All right. We are back better than ever. And tonight's topic is we're going to jump into concavity and the second derivative test. And just to give you a visual image, I think this picture does a really nice job right here. And what you'll notice is this portion of the curve is concave up. And we've been talking about smiley faces and frowns lately. And then we've got what we call a point of inflection right here. And from this point all the way until here, we're concave down. We've got a second point of inflection. And then from here, we're concave up again. So by definition, and we'll get into this later, a point of inflection is any point on the graph where f changes concavity. Well, similar to last night when we looked at relative extrema, I'm going to try to be real official with some of our definitions here so that we get more and more comfortable with some of this fancy lingo. And, in years past, I might have tried to water this down a little bit, but this year we're going to try to amp it up. So first and foremost, we're going to define f as a differentiable function, a function whose derivative does exist over a certain interval from a to b. Now, in fact, I see a little contradiction there. Open means I should have parentheses around that interval right there, okay? Otherwise, if I go brackets, then I got to say closed. Okay, now, if the graph of f is concave upward, we'll say, okay, on that open interval from a to b, then all of the tangent lines are going to lie where? You got it, below the curve. In fact, I think I cut off the word curve there. But if I'm drawing a picture, let's draw a really nice concave up parabola. No matter where you try, you pick any point on this curve and you try to draw a tangent line anywhere on that curve, and every single one of those tangent lines is going to lie convincingly below that curve. Okay? And just the opposite of that is going to be true as well. Again, we could say f is some differentiable function over the open interval from a to b, and if the graph of f is concave downward, then try to, if I could spell, there we go, on the open interval, try to visualize where all of your tangent lines are going to lie. In this case, they're going to lie above the curve, and if we try to draw that picture, here's something that's concave down. And let's see, you pick any point here, 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 and we're above, above, and above. Now, where they're going to try to trick you is they're going to try to say, like, f's increasing. And, is that enough information to determine whether the tangent line lies above or below? And it's not. I think in both of these pictures you could see some pictures where f might be increasing but the tangent lines are below, and then there's other times where f could be increasing and the tangent lines are above. So just if we only know whether it's increasing or decreasing, that doesn't tell us where the tangent lines lie. We've got to know f's exact concavity in order to determine whether the tangent line lies above or below the curve. So let's talk a little bit about the second derivative and how it's tied together with concavity. So first of all, we could define the second derivative is the rate at which the first derivative is changing, right? Or another way to say it is the second derivative is the rate at which the rate of change is changing. And so it can become a tongue twister in a hurry. But what we basically want to get to is this. If we know that f is concave up, then f double prime is going to be positive. All right? And the converse of that is true, just like yesterday. If we know that f double prime is positive, then that implies that f is concave upwards. Okay? Let's see, just the opposite. If we know that f is concave down, then what must be true? Well, that implies that the second derivative is negative. Or the converse of that, if we knew for sure that f double prime was negative, then that would imply that f is concave downwards. Okay, we'll go back to some formal definitions here. Point of inflection, as we kind of hit on that first slide of the night, is a point on the graph of f when the concavity of f changes. Okay, and so let's say if at x equals c is a point of inflection, then either f double prime of c equals 0, or f double prime of c is undefined, or in other words, doesn't exist. So that kind of rings a bell from last night. That's what we would call a critical point. And what else has to happen? Not only does the second derivative equal 0, or we would say doesn't exist, and f double prime has to change from positive to negative, or from negative to positive. In other words, f double prime has to change signs. Okay? And we're not real particular. We don't care if it changes from positive to negative or negative to positive. I know yesterday when we were talking about relative maxes and mins, we were really particular about what order it went from or changed from. And today we don't care. As long as f double prime changes signs, boom, we got a point of inflection. Now watch out for this monster bear trap. Just because f double prime of c equals 0, that in and of itself does not guarantee a point of inflection. It just suggests that there may potentially be one there. We'd always have to confirm that with a sign chart. The AP or College Board published a few years ago a list of the top 10 mistakes they see on a yearly basis. And on that list was this mistake right here. The students were just assuming that because the second derivative was equal to 0, that then guaranteed a point of inflection, and that's not necessarily true. All right, let's dive into our first real fun live example here, and I'm going to create a little space above this because what I want to talk about is when you're reading a sentence and you see something like point of inflection, or if you see them start to talk about concavity, whether it's up or down, it don't matter. All three of those phrases are indications that we need to get on that second derivative as fast as possible. So luckily here I've got a really friendly polynomial, which suggests that all I need is some really quick painless power rules. There's my first derivative, and then the second derivative is just the derivative of the first derivative, so I'm going to have 12x squared minus 24x. And now what I'm going to do is I'm going to set this equal to 0. Now of course we can already confirm that the second derivative will always exist. There are never any points on this function that are undefined. Take out my GCF of 12x, and by the time I tee that bear up, we're going to have two potential points of inflection, one at x equals 0 and one at x equals 2. Now to confirm that those are truly points of inflection, we're going to follow this up with a real nice smooth sign chart that's continuous from negative infinity to positive infinity. Remember, in this case, we're going to put f double prime on top, and we're going to use those values to describe the behavior of f. And so first things first, I'm going to pick something like a -1, and I'm going to substitute that -1 into my second derivative right here. You could plug it into this one, but for me it's easier to go here. And when I do that, I get a -12 multiplied by a -3, which is indeed a negative something, okay, which describes f as being concave down. All right, then I'm going to pick anything in this interval, which would for me is a +1. Let's see, 12 times 1 is positive, 1 minus 2 is negative, a positive times a negative is, oh my garage, that just, how did I miss that? Hopefully you were at home screaming at your computer. A negative times a negative is now positive. Oh my garage, pretend that did not happen. Growth mindset, right, Hill? It's okay to make mistakes. And then, let's see, this would be concave down. And then let's see if I can get this last one right. I'm going to pick a number 3. You can pick anything between 2 and infinity, and we'll plug the 3 into here and then here. And I'm getting, let's see, a positive 36 and a +1. Multiply a positive times a positive, and we're back to positives here. Okay, so the behavior of f we'd say is concave up. And so a couple of justifications that I want to go over. First and foremost, we could say f has a point of inflection at x equals 0 and x equals 2 because, watch how I justify this, f double prime changed what? What changed? Changed signs. In other words, we went from positive to negative, and then we changed from negative to positive at those specific points. Now if you want to get specific and talk, say like, yeah, f double prime changed from first positive to negative at 0 and then change from negative to positive at 2, feel free to do so. As far as concave up and down, I would say f is concave up we'll say from negative infinity to 0, as well as union, that's a union sign, from 2 to infinity, because why? Because f double prime is positive. And then last but not least here, f is going to be concave down from 0 to 2, because f double prime is what? Negative. Now, a really interesting thought is, and maybe you're sitting there wondering, golly gee, I wonder what this function f looks like. And you can start to get this glimpse of, if we took everything that I just did here on this problem and combined it with everything we learned yesterday with regards to the first derivative test and relative maxes and mins and when f's increasing and decreasing, we could really synthesize all that information together and come up with one heck of a graph. And when I did that, I got something, if I draw my axes here, I got something that looks like this. We were concave up until the graph passed through the origin right here. And we had that first point of inflection at 0. And let's see, we then changed concavity to concave down until I hit, we'll say that's 2 right there. And that was my second point of inflection. And then from there, we were concave up again, and it crossed the x-axis at 4. So you get a really nice graph where you see it's concave up, stop, change direction, concave down, stop, change concavity, and we're concave up to infinity. Now here's a much more complicated function. What we've got here is what we call a rational function. You'll notice a numerator, denominator, and we're looking for all points of inflection as well as intervals when it's concave up and down. So when we see those phrases, we're automatically thinking second derivative as fast. Get your hands on that second derivative as fast as you can. Now we're going to cheat a little bit on this one, but first and foremost, I want you to notice that because of the denominator here, x squared minus 4, I know that there's vertical asymptotes at x equals plus or minus 2. Okay, so I've already got that in my back pocket. And I know there's going to be a horizontal asymptote at power fight, 1 divided by 1, y equals 1. Again, just stick that in your back pocket, just a good habit to get into. So as I buzz through my quotient rule for my first derivative here, okay, and I'm going to go on the fast side. We're thinking low d high minus high, got to get parentheses around him, d low, all over low squared. All right, and by the time you distribute and combine like terms in the numerator there, I'm going to get a first derivative of negative 10x all over x squared minus 4 squared. Okay, now that's only, we did all that just to get the first derivative. All right, and now we're going to repeat, we're going to reapply the quotient rule. I'll switch colors here so hopefully it stands out. The second derivative is going to be more quotient rule. So I'm thinking low d high minus high. Now the d low is going to be a little chain rule, so I'm going 2x squared minus 4 to the first times 2x all over low squared, which makes the exponent now what? Yeah, it should be a 4. And again, we're going to do some distributing and all sorts of fancy stuff, and we're going to combine like terms, and we're going to get this. Okay, I got a 10, I got the quantity 3x squared plus 4. Now that plus sign is going to be very significant here in a moment. And I did get a cancellation, and I had x squared minus 4 cubed here. And it don't really matter whether, you know, essentially for us today, it don't matter what power it's raised to, it's going to give us the same result. Now we talked about setting this bar equal to 0. Well, what happens is you run into imaginary numbers because you end up subtracting this 4 to the other side, divide by 3, and you try to take the square root of a negative and you get imaginary. So in other words, what you could put in your notebook is this second derivative here never does actually equal 0. Okay, so there's no critical points there. However, now ask yourself, will the second derivative ever be undefined? And again, we're looking here and we're saying, well, yeah, it's undefined at plus or minus 2. So that's my sign chart. So in fact, here's the catch. The function might change concavity at negative 2 and positive 2, but we'll never say they're points of inflection because why? Think about what we did at the very, very beginning of this problem. Think about what I asked you to put in your back pocket, and it was those vertical asymptotes, right? So f might change concavity, but they won't be points of inflection because, well, quite simply, no point exists on a vertical asymptote. Let's see, if I test a negative 3, I am going to get, let's see, I got a positive number, therefore f is concave up. I tested 0, and I got a negative answer. F's going to be concave down. And let's see, then I tested a positive 3 and got a positive answer, so F's concave up. If we try to synthesize everything that we've got so far, we said we've got a vertical asymptote at -2, vertical asymptote at +2, and we also said there was a horizontal asymptote at 1 because of the power fight. And we could, let's see, we know we got to be concave up. Now, how did I know it sat above the asymptote as opposed to below it? Well, I took like a -3 and I just substituted it back into the original function f, and I knew it was above. And then I could do, let's see, I know we're going to sit below here, we're concave down, and then we're back to being concave up, and we're above that horizontal asymptote. Now, the last major concept we're going to flirt with tonight is called the second derivative test for relative extrema. And we'll compare and contrast that to what we did yesterday, which was called the first derivative test for relative extrema. Now, you're probably sitting there thinking, hey, Hill, I had a great time on the topic yesterday. I was very, very comfortable with the first derivative test. Why do I want a second derivative test? And first of all, great. I'm glad that you were comfortable with it. However, there's going to be questions throughout the exam where one test works better than the other. And if you know which test to use, you're looking at saving yourself anywhere from 2 to 5 minutes just by knowing which test works best for certain problems. And then I'm going to show you throughout the year, I'm going to show you certain problems where like maybe only the second derivative test works on a certain problem, or vice versa. Maybe only the first derivative test works on certain problems. And so we've got to really have our antennas up to be able to catch when that applies. So first and foremost, our first definition here, condition number 1. There's 3 conditions, and we need to be comfortable with all 3 of them. If I told you that f prime of, say, c equals 0, okay, first of all, that guarantees the existence of what? Yes, a horizontal tangent line. And simultaneously, f double prime of c was some positive number, right? Which means, let's describe what that just said. This tells me I've got a horizontal tangent line, and this says that we're concave up simultaneously. Then we would then say f is guaranteed to have a relative minimum at that point. Now, what does that look like visually? Okay, draw something that's concave up, and then on that picture, identify the one point where the tangent line would be horizontal. It would be this point right here, right? And what's special about that point right there? It's a relative min. Bingo. Okay, let's see. What's next? Let's say, well, what if I said, okay, let's just go prime there. F prime of c equals 0 again, but this time maybe the second derivative of c is now less than 0. What did we just say? We've got a horizontal tangent line and we've got something that's concave down. If that's true, then f is guaranteed to have a relative maximum at that point. How do we prove that? Well, let's draw a picture of something that's concave down. On that picture, I want you to find the one and only point that has a horizontal tangent line. That would be right here. And there's the horizontal tangent line, slope of 0. And you'll notice what's true about that point just happens to be a relative max. Now the third condition, I did mention there's 3 conditions. The third condition says, well, if f double prime of c happens to equal 0, then this test fails. Okay, and that is what we're really trying to say. F might have a relative min, might have a relative max, or neither. In such cases, we're going to revert back to what? The first derivative test. Now, what do you mean it might have neither? Well, a good example is maybe consider x cubed. So what's going to happen here? X cubed kind of flattens out for a second and then turns back up. And so what you'll notice is at this point right here, f prime equals 0 because there's a horizontal tangent line right there, slope of 0, and simultaneously f double prime equals 0, and you'll notice the change in concavity, and that's where the second derivative test fails and or is inconclusive. So here's our last example for tonight, and to do it justice, I should probably do more than one example of the second derivative test for relative extrema, but at the same time, I know both you and I, we don't want this to be a 50-minute video, so we're going to try to do a happy medium, and we'll get more practice tomorrow. So to find all relative extrema, Yesterday, we tried to answer this question using the first derivative test. Today, we're going to try to answer this question using the second derivative test. Hopefully, in both cases, we should get the same answer. And like we talked about, there's going to be pros and cons to both tests. So first things first, I want to get my hands on the first derivative. And in other words, my first step is to identify all horizontal tangent lines. So we're looking for all horizontal tangent lines. In other words, we want the first derivative to equal 0. The big difference is today, we're not worried about the first derivative being undefined like we were yesterday. We're just looking for horizontal tangent lines here. And so when I do that, I'm going to get negative 15x to the fourth plus 15x squared, set it equal to 0, pull out my GCF. Let's see, I'm going to go 15x squared, leaving me with negative x squared plus 1. Or if you feel more comfortable, you could turn that around and say 1 minus x squared, difference of two squares, or really we could just tee it up right here and we'll say x equals 0 and x equals plus or minus 1. So there are potentially three relative extremas, combination of maxes and mins. Now, in order to test those, we're going to evaluate them at the second derivative. So here we go. Find your second derivative. Again, pretty painless. I'm looking at this function right here, and I got negative 60x cubed plus 30x. And I'm not worried about setting this equal to 0 or any such thing. I'm just going to take these three horizontal tangent line points and plug them into the second derivative one at a time. Okay, first things first, I'm going to plug in f double prime of negative 1. And let's see, we'll get, I'm really just trying to figure out if I get a positive or negative answer. And I think this turns out to be positive 60 minus 30. And I'm definitely getting a positive answer. So what we know is the function's concave up with a horizontal tangent line, and we've got a relative min at x equals negative 1. All right. Let's see, let's try 0, which would be negative 60 times 0 to the third plus 30 times 0, which in this case is 0. And so what we have is we have an inconclusive answer here. And most likely what we're going to find out, and I'm going to save us some time, I'd go back and use the first derivative, and what we're going to find out is there's neither a max or min. Now you're wondering, what did I do to go back to the first derivative test? Well, what I did is I just confirmed that the first derivative didn't change signs as 0, and so there's a big old neither there. There's sometimes we call it a false critical point. And then last but not least, let's see, let's plug in a positive 1. Negative 60 times positive 1 cubed plus 30 times positive 1, and that's a negative number. And what you'll see here is because the second derivative is negative, then f is concave down. We know there's a horizontal tangent line at 1, therefore there is a relative max at x equals 1. Ladies and gentlemen, that's the second derivative test, and my goal, over the next couple of, besides a lot of practice tomorrow, is I'm going to try to showcase some different problems where maybe only the first derivative test works or only the second derivative test works, and give you some keys to know when those are true. All right, good luck. Have a great night. We'll see you tomorrow.